Check it out now, y'all.
NanoHub U, online instruction.
Okay, welcome back. We're going to discuss in this lecture the energy eigenvalues and eigenfunctions for a finite square well in one dimension. This lecture is a little bit more mathematically challenging than the previous one because the solutions are not analytic as they were in the prior lecture. In order to understand this, you're going to have to follow along rather carefully. You're probably going to have to do some algebra on your own to check the various steps that I've written down in these slides. So, what is the premise for this discussion? Well, the premise is that in the real world, it's very hard to get a square well of finite length in infinite height. That often does not happen. That's really a toy model. It's much more likely that you can create experimentally a region in space that you can confine a particle. The length of that region of space is going to be L. Now what we're going to do is we're going to say that the barrier that confines the particle has a height v0. And it's not going to be infinite as it was in the previous lecture. So this potential energy term in Schrödinger's equation, the U of x, right, that we're going to use in Schrödinger's equation is now going to be given by this piecewise continuous function, which is basically 0 between minus L by 2 and L by 2, and then jumps up to some finite value of v0 for all values of x. And the problem is going to be exactly the same. The premise of this discussion is going to be exactly the same as in the previous lecture. We're going to take a particle of mass m, we're going to drop it into this well, we're going to confine its location to within minus L by 2 by plus L by 2, and we're going to ask what are the allowed energy states for that particle in that well. So what's the big difference between this discussion and the one in the previous lecture? And the big difference is really the boundary conditions on the wave functions. If you recall in the previous lecture, the boundary conditions were such that the wave function had to be equal to 0 at the boundaries of the well, right? And that was simply because the well was infinitely high. Now we've got a piecewise continuous potential, right? In principle, the wave functions do not have to be 0 at these boundaries of the barrier, right? And as a consequence of that, the allowed energy levels are going to shift. They're not going to be at exactly the same locations as they were for the infinite square well. And it's kind of useful to sketch the wave function that we expect just based on intuition. For the lowest energy state, and that wave function would be a symmetric wave function, so it would be symmetric about x equals 0. It would resemble a cosine function, but as the wave function approaches the boundary regions, there's no constraint that it needs to go to 0. It can actually tail off. It actually will exponentially decay to 0 as we go to values of x which are far from the boundary region. So this piecewise continuous potential then gives rise essentially to 3 piecewise continuous wave functions. We'll call those wave functions psi3. Psi1 will be the wave function in the middle region of the well, and then the wave function psi2 will be for values of x greater than 0. And what we're going to do is we're going to write down possible solutions of Schrödinger's equations for psi1 and let's say psi2. We'll focus on positive x in this discussion, right? We'll write down possible solutions for psi1 and psi2, and then we're going to insist that both the wave function and its derivative be continuous at this point x equals L by 2. That's the boundary condition that you have to put into all of these problems. And then we're going to see what conditions this requirement of continuity in psi and continuity in the first derivative side, we're going to see what conditions those impose on the allowed energies of the electron state in this well. Okay, so that's the big plan, the big picture. First thing we have to do is we have to solve Schrödinger's equation using this piecewise continuous interaction potential, this potential energy barrier that we sketched in the previous slide. And so there are two regimes that you have to recognize. This is something you've got to put into the problem based on the specified potential well that's given to you. So for the region of x between minus L by 2 and plus L by 2, the interaction potential energy is by definition 0. So Schrödinger's equation for this region of x simplifies down to a much easier differential equation. We define a parameter k in terms of this 2me over h bar squared, and that allows us to write Schrödinger's equation in simplified form for this region of x. Okay? When we get outside of x greater than L by 2, so as soon as x gets beyond the confines of that potential well, then the interaction potential barrier jumps up to V0. Right? That's the height of the well. And so V0 now has to be put into Schrödinger's equation when x is greater than L by 2. And that implies that if we define another parameter called kappa, given by the difference between V0 and E, then we can write Schrödinger's equation in this region of space in this form. And notice the only difference here is that up here we've got plus k squared, down here we've got minus kappa squared. So there's a change in sign of this constant that comes in. And what we need to do now is we need to look for possible solutions of the wave function in these two regions of space. And so we have to solve Schrödinger's equation for x between minus L by 2 and plus L by 2. We've got to solve another differential equation that's derived from Schrödinger's equation when x is greater than L by 2. Now, the solutions to those equations can be actually written down analytically. They rely an awful lot on the insight that we got when we discussed the infinite square well barrier. And in particular, what we're going to expect to recover in this discussion of the finite square well is we're going to expect to recover these symmetric and anti-symmetric wave functions that we discussed in the infinite square well problem. The only difference is that the wave functions are going to be altered as the value of x gets close to the width of the barrier, L by 2. The way that normally these differential equations are solved is you make an intelligent guess for the wave function, and then you use that intelligent guess and see what the consequences of it are when that solution is plugged back into the differential equation. And so we're going to follow that same approach here. The wave function psi2, which describes the de Broglie behavior of that particle when x is greater than L by 2, that's going to be given by this wave function psi2. It's going to be a constant c, and it's going to decay exponentially as e to the minus kappa x, right? And that implies that as x gets larger and larger, this wave function goes to 0, which is something that we really insist on all these problems having that characteristic. Likewise, the wave function psi3 is going to be given by e to the plus kappa x. And so now as x gets less than minus L by 2, right? So here x is always a negative number, right? This will exponentially go to 0 as x increases without doubt. And then in the region of the well itself, we're going to rely on the sine and cosine solutions that we already have discussed for the infinite square well potential. So That's those are the trial wave functions. It's not guaranteed those wave functions are going to work. You have to actually put them back into the equations and see if they solve the differential equation. Well, of course they do, because otherwise I wouldn't be up here talking about them. But in principle, you first have to write down a solution and then test that solution to find out what conditions the differential equation imposes on the wave function. So let's see. Let me focus on boundary conditions, and let me just first focus on the symmetric wave functions. The symmetric wave functions involve the sine function or the cosine functions for psi. And what we're going to insist on is we're going to insist on the wave function and its first derivative be continuous at x equals L by 2, right? So this simply means that the symmetric solution at x equals L by 2, just to the left, just to the right of the boundary, we're going to use the wave function psi 2 here, right? To the left of the boundary, we're going to use the symmetric solution cosine of KL by 2. And so if these two wave functions have to match at L by 2, then we have this condition that has to be satisfied, and that gives us one equation. The other equation comes about by insisting that the derivative of the wave function at L by 2 matches. And when we impose that condition, we get a second equation. And we're going to use these two equations to impose restrictions on the allowed values of this parameter k. And if you recall from 2 slides ago, this parameter k is also related to the energy E for the particle to have. So if we find that k is restricted, then also the electron energies E are restricted. The way this solution evolves is we just basically divide 2 by equation 1, right? That eliminates this unknown constants C and A, right? So they drop out, and we've got a condition that has to be satisfied if these two boundary conditions are going to be satisfied. And this is referred to as a transcendental equation, right? It's a complicated equation. It's complicated because it involves tangent of k on the left-hand side. It just involves k, 1 over k on the right side. And, so somehow we have to find the values of k that satisfy this transcendental equation. The strategy we're going to employ in the next slide is we're going to transform the right-hand side of this equation so it contains the same parameters as contained in the argument of the tangent function. So we'd like to rewrite the right-hand side so we've got a KL by 2. And then we'd also like to introduce the ratio of V over V0 so it explicitly appears in this equation. And these are just strategy decisions that are made. And then you have to go about doing the arithmetic and algebra to carry out those goals. So I worked that out in this slide. It's just straightforward algebra. I take the definition of kappa over k and I expand it, and then I start to rewrite it so that I get KL by 2. And I also pick up this parameter V0 in the expression. And after a few lines of algebra, what you find is that the equation up here right, can be rewritten in terms of a new variable theta. This new variable theta is just KL by 2, right? And then there's a constant parameter theta naught. Theta naught involves the mass of the particle, the length of the well squared, and the depth of the well, which is this parameter V0. So once I specify V0, once I specify L, I basically specify theta 0. So in this transcendental equation written in this way, Theta 0 is just some constant number, which is specified by the problem I'm trying to solve. You'll notice that this transformation of variables has accomplished this goal of rewriting the argument of the tangent function in terms of the argument itself. So now theta appears on both the left and right hand side of the equation that we're trying to satisfy. This is the approach for the symmetric solution. There's an equivalent, exactly analogous approach for the anti-symmetric equation. The only difference is now, instead of having tangent functions, we have cotangent functions, but the form of the equation that must be satisfied is exactly the same as for the symmetric solutions. So the trick now is to solve these transcendental equations for theta, right? Once we have solutions for theta, well, let me back up. What we have to first do is we have to specify theta 0. That's determined by the shape of the well. Once we specify theta 0, then we have to solve these two transcendental equations for theta. Once we have allowed values of theta, that allows us to decide what the allowed values of k are. Once we have the allowed values of k, then we can calculate the allowed values of energy E for this problem. And so there's a number of ways to do this. I just basically what I just said I write down here. Right, we have to do it for the symmetric and anti-symmetric solutions. The issue is how to solve an equation like this, right? How are you going to solve that? This is the solution for this is the condition for the symmetric solution. This is the condition for the anti-symmetric solution. How are you going to solve those two equations? Well, there's a number of ways you can do that, right? One way is you can sit down and you can write a MATLAB code or a C++ program to solve those differential equations. A second way is you can find a dedicated app on the web that actually is geared towards finite square well potential. And I refer you to a website which basically solves those two transcendental equations and allows you to then calculate the allowed energies, and also gives you plots of wave functions for a square barrier, finite width. You can specify the depth of the barrier and the width of the barrier. Right, so if you go to this website, you can get a sense and a feel for how these solutions work without having to do any work at all. It's all programmed in. And then the way we're going to discuss in lecture is we're going to graphically solve those transcendental equations. And we're going to do that by first specifying this parameter theta 0, and then we're going to find out what values of theta are required in order to solve the transcendental equations. So there's at least 3 ways to work through this. The graphical solution is just intended to allow us to discuss the results of a particular problem within the confines of this lecture. Most people that are interested in this will actually write their own code that solves these equations for the problems they're interested in. So let me remind you what we're trying to do here. We're trying to solve this transcendental equation. We're gonna let theta be plotted along the x-axis. Recall theta is equal to KL by 2. And on the y-axis, we're going to plot this the square root term over here. This square root of theta naught squared over theta minus 1. That's plotted in this direction here. Right? This is the f of theta. Right? And what we want to do is we want to find out for what values of theta this equation is true. Right? This is an odd-looking function. The tangent function or the minus cotangent function are a little bit easier to plot, So we're going to make a plot of tangent minus cotangent. We're going to make a plot of this. And whenever the plots of tangent or minus cotangent intersect the plot of this, those are possible solutions. Right? So that's a graphical approach. And that is actually carried out in this diagram, which is going to require you to think about it for more than a few minutes, right? What I do is I plot the tangent and the minus cotangent, right, sequentially, right, for different values of theta. And then I also plot the square root term, which is this guy down here. Whenever the square root function f of theta crosses the tangent or minus cotangent plot, and those crossing points then define the possible values of KL, right? So in this case, there are 4 possible solutions for KL. And once I specify those functions for KL, I can then read over and I can find out the values of this function, theta naught squared over theta minus 1 square root of. So this is the graphical solution. I expand the solution to provide a little bit more detail. Here I just arbitrarily pick 3 values of theta naught. I pick theta naught equals 1, 3, and 5. In a few minutes, we'll discuss what parameters are required to produce these particular values of theta naught. But once I specify theta naught, then I can plot the square root function, as I've got drawn here. Right, so I can get a red curve for theta naught equals 5. I can get a green curve for theta naught equals 3. I get a blue curve for theta naught equals 1. And the intersection of those red, green, and blue curves with the tangent or minus cotangent plots then specify the allowed values of k, L by 2 for the particular parameter theta naught that we specified. So in this case, let's focus on theta naught equals 5. Right? Theta naught equals 5 has actually 4 distinct solutions. I can read from the plot the allowed values of KL by 2, right? And I can also then read from the plot the allowed values of this square root function. And those allowed values are then going to tell me the allowed Ks and the allowed energies for a particle of mass m in this well of finite height. So it's a complicated process. You're not going to understand it unless you actually sit down and try to work through some of the steps on your own. But hopefully these slides will be a useful guide to make sure you're on the right track. So let's put in some numbers and see how this all plays out. Again, we're going to consider an electron with mass m sub b. We're going to drop that electron into a potential well. We're going to say that the length of the potential well is 5 nanometers, just to pick a value. We're also going to say that the depth of the potential well is 0.153 electron volts. Now, why did I pick 0.153 electron volts? Well, I picked 0.153 electron volts because if you evaluate this parameter theta naught, you'll find it's actually equal to 25, and that just simply means theta naught for these parameters is equal to 5. That value of theta naught equal to 5 just matches the solutions that I've already plotted in the previous graph. So that's why the parameters were chosen for what they are. You can read from that plot the allowed values of theta, right? You can then find the values of tangent and minus cotangent that satisfy these particular values of theta. Once I know theta naught, then I can then calculate the energy E for each energy eigenvalue in terms of the ratio of V naught over theta naught squared times this parameter KL by 2 quantity squared. So see, the KL by 2s are fixed by the solutions of Schrödinger's equation. Once those values of KL by 2 are fixed, they specify the allowed energies for the problem at hand. You can go through the arithmetic and you can calculate these energies. These are the four solutions for an electron in that potential well. The energy eigenvalues again are labeled subscripted by the quantum number n. They're 0.01 eV, 0.041 eV, 0.089, and 0.143 electron volts. So those are the only allowed energies that electron can have if it's placed in that well. There's only four solutions to Schrödinger's equation, and that's in marked contrast to this infinitely high potential well, which had an infinite number of solutions, right? The solutions varied as n squared. And so it's kind of useful to compare the eigenvalues, the allowed energies for an electron in an infinite square well of the same length as an electron in this well of finite height, but also the same length. In both cases, the length is equal to 5 nanometers. And what you see is, when you do that comparison, this is kind of interesting, right? You see that the lowest energy state doesn't shift much, but by the time you get up to n equals 4, the allowed energy for the finite potential well is about half that for the infinite potential well. So graphically, I tried to show the comparison, right? And it's a very interesting comparison. These are the results for the infinite square well using these parameters. These are the results for the finite square well. You can see that the shift at the lowest ground state energy, the shift is very small, but by the time you get up to the fourth energy level, right, there's quite a large shift in energy. These quantized energy states are bound, right? And you can talk about their energies in two ways. You can define the zero of energy as being down here, in which case the energy of these electron states are measured from the bottom of the potential well. Conversely, you can talk about binding energies. In other words, how much does the energy drop once the electron is placed in this finite square well? If you talk about binding energies, then you define the top of the well as equal to 0. That means that the bottom of the well would be minus 0.153 EV deep, right? And then these energy levels would all be negative, right? Because they would then be designated as bound states in this potential well. You will see both types of notation used, and it's important for you to understand what those different types of notations are all about. The other thing we can do is we can plot the allowed wave functions for each of these energy levels. I just plot the first three here, right? You can see now that the electron state is actually leaking out into this forbidden region of the potential. This is again distinctly different from the infinite square well barrier problem that we solved in the last lecture. The electron state actually has a certain probability of leaking out and being found in regions greater than the plus minus L by 2 that defines the width of the square well. So if you go back and you remember the discussion about probability densities and what the probability is of finding an electron in a certain region of space, you would have to square these wave functions and then multiply the square of that wave function by the width delta x of a certain region in space here, and you would find that there's a non-zero probability. If you went in and you did an experiment and tried to measure the position of that electron in that potential well, there would be a finite probability that the electron would actually be outside of the well. And this is a consequence of the fact that when electrons are treated, or when particles are treated as waves, right, they extend over regions of space which are not accessible to classical physics. So I think I've got to stop. I've ran over a few minutes from the 25-minute time slot I like to keep these lectures confined to. But this is the discussion of the finite square well. It's a much more realistic problem than the infinite square well. And it's important for you to understand, at at least the steps involved in trying to find these energy eigenvalues and to find these allowed k values for this very classic problem that you find worked out in just about every quantum mechanic modern physics textbook that you'll pick up. So come back next lecture. We're going to talk about a third model for the interaction potential of a particle. It's going to be a quadratic potential, and it's going to mimic a particle attached to a quantum spring. And we'll discuss the solutions for that in the next lecture. So thank you very much, and we'll see you later.